Assalamu alaikum. So I'm just waiting for people to join. So today we shall be studying discrete Fourier transform, and this almost is our last topic. I still do need to cover which is not really included in the course, but Rima's exchange or Parks-Maclaurin algorithm for filter design, and I'll spend some time on it, but I want to start learning about the discrete Fourier transform, and it's a very important topic, and that this topic will lead us to discrete the fast Fourier transform. So discrete Fourier transform. So discrete Fourier transform is an important topic as it leads us to fast Fourier transform, and this is the computational algorithm to compute discrete time Fourier transform. It's a little bit confusing, like the terminology which is used in the book or in signal processing, because we have one is discrete time Fourier transform, the other one is discrete Fourier transform, the third one is fast Fourier transform. So you need to be know these three different terminologies: discrete time Fourier transform, discrete Fourier transform, and fast Fourier transform. Discrete time Fourier transform is what we studied in chapter number 2. Okay, and it was x exponential j omega is equal to summation n goes minus infinity to infinity x of n exponential minus j omega. This is the formula for discrete time Fourier transform, and you must be remembering the inverse of this, because a transform should be ideally should have an inverse as well. So it is 1 over 2 pi minus pi to pi x exponential j omega exponential j omega n d omega. Okay, this is a very important transformation in signal processing, which is called discrete time Fourier transform. The issue with this transformation is that this omega is a continuous variable, and that's why the integration sign is here, continuous variable. So this omega is a continuous variable, and we know if there is anything which is continuous, so we cannot put it in a computer memory. Computer memory is a discrete memory, so there is no way for a computer program to compute x exponential j omega. And similarly, there is no way for a computer program to convert or to calculate the inverse discrete time Fourier transform using this integration. You got to do some approximation. So this limitation primarily leads us to discrete Fourier transform. It's basically an algorithm to compute this summation, where we know that omega is continuous. Omega has to be discretized, and once you discretize omega, it becomes discrete Fourier transform. And that is perhaps the reason calling it discrete time Fourier transform, as if it is continuous, and it is discrete Fourier transform because it is discrete both in time and in frequency. So how can you discretize omega? It's simple to discretize omega because omega is something that varies from minus pi to pi, we know. Fourier transform is a transformation where it is periodic over minus pi to pi. Or if in us, if you we are more like, we know that Fourier transform is Z transform on a unit circle. So we know this as well. So this is a unit circle. So Fourier transform is Z transform x of z for r is equal to 1, z is equal to exponential j omega. So this is the relationship between Z transform and Fourier transform. And because you cannot, absolutely no way for you to just calculate the discrete time Fourier transform as a continuous variable of omega, so you have to discretize. So very simple to understand that you say discrete. You say I will calculate it at discrete intervals in time. And how can you calculate it in discrete interval in time? Obviously, you can calculate it in discrete interval in time by putting value of omega, different values of omega. First putting this, or you can consider this as it goes from zeros to pi. As you know, it is continuous and periodic. So either you consider from minus pi to pi or you consider from 0 to 2 pi. Okay, there is absolutely no difference between the two. So you have this 2 pi frequency till 2 pi, so you can have n points in this, n discrete points. So n discrete point means that you have 2 pi over n interval, right? 2 pi, breaking it down into capital N points, so you have 2 pi over n. So this first value of the frequency will be 2 pi over n. The second point you calculate the frequency, it is 2 into 2 pi over n. This is the third one. Third one will be 3 into 2 pi over n. So you can just have like discrete intervals of time, keep putting these values here in omega, so you get this. So we can just safely say that discretization means that you have these discrete points on the unit circle, and how many, it's up to you, that how many you afford. You can have 100, you can have 1000, you can have 10,000, you can have 1 million. It's up to you that how closely you want it to mimic the continuous curve. It's up to you, like if you have more computational power, because primarily FFT or DFT is used for analysis. So it's mostly up to you that how many points you want your 2 pi region to be divided, and you can just calculate it for those many points. Okay, usually it should be more than the number of points in the signal, like x of n, or at least as many as there are number of points in the signal. So this is a kind of a rough gauging this is that at least you should have n points if you have n points. And then there is another limitation in this equation, that you cannot deal with infinity in your computer program, so it has to be a finite amount of data, which is okay because we in reality want to deal with only finite amount of data. If it is signal which will keep running, so we only take finite chunk of data and we discretize it. So one limitation is this. The second limitation you need to deal with is the finite, that data has to be finite. You cannot just have infinite amount of data which a computer memory cannot keep. So it's very logical. So both these limitations are very logical. So if you deal with both these limitations, your formula becomes summation n goes from 0 to n minus 1. Okay, n points only of x of n. As I mentioned, that at least you should have divided the omega exponential minus j, and instead of omega you write 2 pi over n into k. Okay, this is now our new omega. This is our new omega. This is my omega. Once I put k is equal to 0, it is 0, it is my first point. Once I put k is equal to 1, it is 2 pi over capital, and this is my second point. Once I put k is equal to 2, it is my third point. So similarly, just keep going. And once I put n, it is my 2 pi, which repeats itself, like the 0 and pi, they are going to be the same. And I put n as it was in the formula. So n is the same as it was in the formula. So this n. So this formula is called, because now there is no omega, so instead of writing a cumbersome expression exponential j 2 pi k over n, you simply write it as this. So this is the formula for discrete Fourier transform. Discrete Fourier transform formula is written as this. And because now omega is discrete now, so the summation, the integration will change into a summation. And so the formula for inverse, and 2 pi is divided into n parts, so this formula will look like this. K goes from 0 to n minus 1. Instead of x exponential j omega, you put x of k, and you put exponential j 2 pi k n over n. Similarly, omega is changed into discrete, and this will give you x of n. So these are the two formulas now. Okay, so same formulas, because now omega is discrete and your n you are only considering finite amount of data, so it makes sense. Now this formula, so they are the same. So very good. Like we can now, because now it's discrete, means a computer program. It's a very simple computer program. You can perhaps write it again. If it's a good programmer, it will take you 5 to 10 minutes to write a computer program to calculate a discrete Fourier transform. There are two loops. One loop runs over k goes from 0 to n minus 1. Then there is another loop which runs over n goes from 0 to n minus 1, and you are just multiplying, adding, calculate one value, go to the upper loop, calculate the other value. So a very simple computer program, which again would not take you too much time. You can write a program to calculate the discrete Fourier transform or inverse discrete Fourier transform. So this is, so we have actually discretized. And if you look at this formula, this would also tell you that because this is complex and you have n of these multiplications. So n here multiplication and n here. So n points, so you have n multiplications and n minus 1 additions to calculate one value of discrete Fourier transform. For one value, so you need n square n multiplication to primarily compute one value. So n square multiplication to compute all the n values. So this is the complexity of the algorithm. N square values, n square multiplications. Usually we are concerned with multiplication. Usually people are not really worried about addition. And once you learn the course on digital system design, you will appreciate it more, that why multiplication is more expensive than the addition. Because you have so many partial products and you have to add them together, and so that appreciation will come from your course in the next semester. But usually people talk about multiplication. It takes more power and it has more kind of cost in terms of area as well. So n square, complexity of this is n square, and similarly complexity of this is also n square. So these are the two formulas. And so now whatever we have studied in discrete time Fourier transform in chapter number 2 has to be redone using these formulas. Okay, so what have we studied? If we go back and remember, I think we studied properties. Okay, so if you remember, linearity and multiplication in time is convolution in frequency, shift properties, and so we studied several properties of, we said it's a mathematical formula, so it adheres or obeys many properties. So let's discuss those properties. And we studied, and I'm just writing those properties here. First was linearity, like if you multiply a signal with A and another signal with B and you add them up together, then its discrete time Fourier transform is going to be the same. x1 exponential j omega plus b x2 exponential j omega. Remember this? So we have actually studied this property which is called the linearity property. And then a property which we have used in solving many questions was delay. If there is a delay in time, it is multiplication by an exponential j omega d x exponential j omega. This is the second property we studied, meaningful properties. The third property was if you multiply a signal with an exponential, then its Fourier transform is shifted in frequency domain. Remember this? Then we have studied convolution in time, multiplication in frequency. Okay, and then there are others, but these four properties are very important properties which we extensively use in signal processing, even in digital communication. So these four properties are very important properties of discrete time Fourier transform. Okay, and now we have, because changed the formula, they may remain as is or they may change, we don't know. So there is a big question mark on the applicability of these properties on the new formula that we have derived by discretizing these two formulas, discretizing these two formulas as these two formulas. So we still don't know whether those properties are valid or not. So one way of validating those properties is that you just put these formulas into those expressions and find out whether these properties are valid or not. But other is another interesting approach that book takes, and I intend to use that approach. And they talk about first they start the chapter on discrete Fourier transform, and they talk about discrete Fourier series. Discrete Fourier series. Discrete Fourier series. Okay, and if you remember about Fourier series only, and you have studied it in so many courses, I know for sure, and still people are not sure that what Fourier series is. Okay, so we have studied this in many courses, and if you remember, in maths there is a course you study this, and complex analysis, complex variable analysis, you study this, and then signal and system you study this. Fourier series. So Fourier series is being taught to you in many courses, more than one or perhaps two or maybe three courses. And the concept is very simple. Fourier series, that if there is a periodic signal, so the condition is the signal has to be periodic. Any periodic signal, as a matter of fact. Okay. So this is a periodic signal, for example. So Fourier series says that for any periodic signal can be split into number of cosines. Number of cosines, or if it is complex periodic signal, the number of exponentials. Okay, and these cosines, one will have obviously there is going to be a DC value. There may or may not be a DC value. For example, here I don't see a DC value. The first is first harmonic, which is the same frequency as the fundamental frequency of this. So there is going to be the first harmonic will have the frequency which is the fundamental frequency, and I'll show you some animation as well. So this is my fundamental, which I can guess and I can plot right away like this. This is the first harmonic. And then it says that there is going to be a second harmonic, which is exactly twice the frequency of fundamental. Then there is third harmonic and fourth harmonic. So possibly only the frequencies which are multiple of the fundamental frequency with different amplitude and phases. If it is a real signal, there will be infinite many cosines with different amplitudes and different phases that will combine together to make any periodic signal. Okay, so if you add two of these, so it start taking the shape of this the periodic signal. So if you add this, you will find out it will be something like this. You see, it start just making the shape of a square pulse. And remember, I put a post on a page that the leading mathematicians of that time would not believe Fourier that this could happen, and they never accepted his paper. Once they died, like Lagrange died, and only then his paper was published. Fourier series paper was published. So if there are more, so then it starts surely but slowly start taking the shape of a periodic signal. So no matter what type of periodic signal you have, you can split it into many cosines. So this is for the continuous Fourier series. Discrete Fourier series is even more interesting, and it says that if you have a discrete periodic signal, okay, so it talks about a discrete periodic. What is a discrete periodic signal? Obviously a signal which repeats itself after some capital N. So for example, this is a discrete periodic signal. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So it is capital N is equal to 8. So this is a discrete periodic signal which repeats itself at every N is equal to 8. It repeats itself at every N is equal to 8. So this is a discrete periodic signal. So there could be anything. If it is repeating itself at N is equal to 8, it is a periodic signal. Okay, it may be something like this. Okay, it could have any shape, but it has to repeat itself after N is equal to some value. And interestingly, a sampled sinusoid may not be periodic, because you may find out though a continuous sinusoid is always going to repeat itself, but it depends at how you have sampled it. You may have sampled it in a way that it is never repeating itself. For example, this is your first sample is here, but this sample is somewhere else, so it is not at the same location because of the sampling interval. So you can always select a frequency where a sinusoid may not repeat itself, though its shape is repeating itself, but the samples are not repeating itself because the way you have sampled it. But it's just not really important what we are studying here. What we are saying that if there is a periodic signal which is repeating itself, a periodic signal which is repeating itself, it can be split into cosines. And why I am saying it is more interesting, because in discrete signal processing, it will exactly have n number of cosines, because continuous is very difficult to prove, because continuous says that infinite many cosines. So who could generate infinite many cosines and then add up together to see whether actually infinite many cosines make up a signal? But discrete is very simple to prove, and discrete says that they are going to be exactly n complex exponential to break up this into, or if it is a real signal, n cosines. But usually for discrete, this is what we use, n complex exponential. So what does it mean? It means that if I have a periodic signal, periodic signal is written as x tilde of n. This is the notation which book uses to show that it's a periodic signal, and periodic is tilde n plus n. Okay, kn for all values of k. So this is a period which repeats itself at every kn. A periodic signal is one, it repeats itself at every kn is a periodic signal. And we are saying, okay, if there is a periodic signal, so you can actually make a periodic signal with period capital N by summing k number of complex exponentials, 0 n minus. So this is important, this summation is important, that only n number of complex exponentials of a fundamental frequency and 2 times the fundamental frequency and 3 times the fundamental frequency exponential j 2 pi n k n. Okay, so this is an important formula, and so this is the these are the exponentials, and this is the amplitude, because it's a complex number, amplitude and phase of each. So all I am saying is that there is going to be n number of complex exponential. First exponential is exponential j 2 pi, let's say n is equal to 4, 0 n. This is my first complex exponential. My second complex exponential is exponential j 2 pi 4 1 n. Then there is a third, which is, now it is the fundamental frequency. This is 2 times the fundamental frequency, and this is 3 times the fundamental frequency. Okay, so these are the 1 2 3 4. So if you put n is equal to 0, you are going to get 0 0 1 1 1 1. So 0 1 2 3. This is my first exponential. The second exponential, if you plot, is going to have a real 4 samples and complex 4 samples, because we know exponential is cosine of this plus j sine of this. Similarly, if you plot this, there are going to be 4 samples, 4 samples, 4 samples, 4 samples. Okay, so there will be 4 samples, there will be 4 samples, there will be 4 sample, 4 sample, 4 sample, 4 sample. Okay, so these are, so this is what the discrete Fourier series says, that any signal with period n, here I have taken 4, it can be split into 4 complex exponentials. 1 2 3 4, 4 complex exponentials, that if you add them up together, you will make up the signal, any signal you have. So any signal can be split into 1 2 3 4. 1 is DC value, okay, then is the first harmonic, second harmonic, and third harmonic, or n minus 1th harmonic. But every exponential will have an amplitude and a phase. Okay, so that you have to compute. So this will have an x0. This is a complex number. This should have x tilde 1. This should have, sorry, x1. This is x2. This is x3. So these are called discrete Fourier series coefficient, or sometimes we call these discrete Fourier series. Discrete Fourier series coefficient, or usually we call them discrete Fourier series. So these are the coefficients. So if you look at this formula, it is saying the same thing, that discrete Fourier series is basically splitting a signal. So this is a signal which is basically a sum of exponentials. That's all the Fourier says, that a signal, if it is periodic, can be split into n complex exponentials, no matter what. If like n is equal to 8, so 8 complex exponentials. You change the shape, the coefficients will change and make the guaranteed 100%. Once you add them, it'll make exactly the shape of the signal. So this is the beauty of the discrete Fourier transform, that n complex exponential guaranteed that they will make the shape of the signal once you add them up together. So the important is to find out these coefficients, because these coefficients are important, and there is this factor which will not leave us. This is 1 over n. So the formula is 1 over n, because Remember, all these formulas are two-way formulas, like they go in both directions. So this usually is the inverse discrete Fourier series, because you are combining them together to make up the signal. And discrete Fourier series is where you find out these coefficients. So there is a formula, and if it's better that I write it here so that you can just. So this is x tilde of k is equal to summation n is going to 0 to n minus 1 x tilde of n exponential minus j 2 by k over n. So you see, this is how you find out the Fourier series coefficients. And if you put this x tilde of k here, it will become x of n. So it's a very simple proof of this formula as well, which I'll not get into. But important is that these are the two formulas, and this formula is called the synthesis formula. And this formula is called the analysis formula. The two formulas are very important formulas, synthesis and analysis formulas. So discrete Fourier series formula. So this is called the analysis, and this is called the synthesis. Discrete Fourier series has two formulas, and because whenever this in signal processing we do this a lot. Whenever there is an expression which is a mathematical expression, we just get into the expression and find out what properties it adheres, and those properties are of interest to us. So same is the case with discrete Fourier series formulas as well, that these formulas primarily adheres many properties, and so we are interested in those properties. So for the first property, as most of these formulas would do, is the linearity property of the Fourier transform. We say, oh, they adhere to many properties, and one is linearity property of the Fourier transform. So this is an important property. And linearity property says that if you have a periodic signal, you can find out its discrete Fourier series as this. So okay, x tilde 1k. These are the Fourier series coefficient. As I mentioned earlier, discrete Fourier series coefficients are called discrete Fourier series. These are the four. If it is 4-point signal, these are the four coefficients. What they signify? They signify the amplitude and phase of 4 exponentials that will add up together in making up of the signal. Okay, so we need to remember that discrete Fourier series coefficients gives you a sense, a feel of that what is the contribution of the 4 harmonics or the n harmonics in making up of the signal. So it gives you really the information about the frequencies in the signal, kind of, because it is just telling you this much is the DC value, this much is the first fundamental harmonic, this is the amplitude of the second harmonic, the third and fourth and fifth. So it gives you the contribution of each in making up of a signal. So this is, so if this is this, and there is another endpoint periodic signal whose discrete Fourier series coefficients or discrete Fourier series is x2 tilde of k. So if you multiply this with a, the linearity says, because the formula is of summation, so the formula is you know that if you multiply this signal with a here, if a, so a will come out of the summation. So it's because the summation is a linear thing, so you know that because of this linearity you just take that constant out. Similarly, if you multiply this with b, so same thing will happen here, that you only need not to recompute the Fourier series coefficients. All you have to do is just multiply the Fourier series coefficient which you have computed. And it also makes sense, like if there is in making up this periodic signal there is a contribution of a cosine. If you amplify it, obviously that cosine will also be amplified. Very simple. Okay, so this is what it says. And then is if you add these two periodic signals together, and remember you can only add periodic signals together if they have same capital N, so that the resultant signal will have the same N. Then obviously the formula is summation, so you add this. So this property is called the linearity property, which says A x1 tilde of n plus b x2 tilde of n gives us A x1 tilde of k plus b x2 tilde of k. Okay, so this is the linearity property, which can be easily proved using the formula, or I can give you a question in the exam where I give you this and its discrete Fourier series, this and its discrete Fourier series, and then I may ask you add them together and find out the discrete Fourier series coefficients of this. So all you have to do is just add them together. Or if I multiply, so you multiply, so you can easily solve questions which deals with linearity. So linearity is one property which is an important property of discrete Fourier series. The second is an interesting property is shift in time. Shift in time. A periodic signal, if you shift a periodic signal in time, it remains periodic with the same capital N for sure. For example, here is a periodic signal. You have 0, you have 1, you have 2, you have 3. 0, 1, 2, 3. Then you again have 0, then you have 1, you have 2, you have 3, and you have 0, you have 1, you have 2, you have 3. So 0, 1, 2, 3, and it is 0. It is going to be minus 1, minus 2, minus 3, minus 4. It is going to be 4, 5, 6, 7. Okay, so this is where the signals start, and this is our fundamental period. Now shifted by 2. Shifted by 2. So once you shift the signal by 2, what will happen? These two will come here, this, and this 2 will get out. So if I put this 0, 1, 2, 3, 0, 1, these are the values. Okay, so 2 and 3 will come in, 0 and 1 will here, and 2 and 3 will go out. Okay, so 2 and 3 will get out of the window, and then is 0, 1. So it is, so the whole thing will be shifted like this. So you will have 1 and 0 and 3 and 2. So it is still periodic. Okay, shifting a periodic signal will make it periodic. That periodicity will not change. Instead of just dealing with this, an easier method is that you put them on a circle. This is your starting point, which is 0. So if you have a signal which says 0, 1, 2, and 3, shifting right means you rotate it like this. So rotate it like this. Okay. So 3 will come here, 2 will come here. So if you rotate it twice, 3 will come here, 2 will come here, and 0 will go here, and 1 will go here. So now it becomes another periodic signal, which is 2301. 2301. Okay. So another way of figuring out that if you are circular rotation or shift of a periodic signal is a circular shift, as if you are just moving in a circle. So one way is you plot a period here, then you plot here, then you plot here, and then you shift. Other one is you just write them on a circle and then rotate the circle, so that if it is twice, so you can consider like the same thing, but you say now this has come here, so you this. So all you are doing is either you shift like this or you change your reference. So both are same. Like if you are using the second technique, is you change your reference. So if somebody says shift, so this is your reference, and 0, 1, 2, 3. And if you are to shift by 1, it will come here. It will 3, 0, 1, 2. Shift by 2, it will come here. It will 2, 3, 0, 1. If shift by 3, it come here. Okay, 1, 2, 3, 0. By this, and 0, 1, 2, 3. If shifting by 4 means that again you are going to see the same thing. So this is called circular shift. So circular shift has a property, discrete Fourier series, circular shift has a property which says that a circular shift is multiplication by an exponential of Fourier series coefficient, like the one we have in discrete time Fourier transform. But remember, it was not circular shift, it was linear shift. So circular shift we understand. I hope that you now understand what circular shift means. So if you shift a periodic signal, it is a circular shift. And if you take its discrete Fourier series, you need not to recompute all the coefficients of a new signal. It's a new periodic signal. You need not to recompute all the coefficients. They are going to be the same as the previous one, only you need to multiply them with the exponential, which is exponential minus j2 pi, and if you're shifting it by m, so it is 2 pi k m over n. So for every value of k, you can figure out that how much this coefficient will change. Put k0, the DC will change. K1, the first harmonic, the coefficient of first harmonic will change. Now this is how you can actually compute. So a shift of a periodic signal is multiplication of its discrete Fourier series coefficients by an exponential. This is called shift in time properties. This is an important again property for discrete Fourier series. Then there is another, remember the third property which we talked about was multiplication by an exponential, and then there was there was another property which we say is important usually in discrete time Fourier transform, and that was multiplication. Almost the same property is in discrete Fourier series, that if you have a periodic signal, okay, and you multiply it with an exponential j2 pi nm and k naught over n. So this is with the k naught frequency. If you multiply it with this, then what will happen to the discrete Fourier series coefficients? They are going to be the same, only they will move, shift, circular shift. They will get a circular shift of whatever k naught is, 1, 2, 3, 4. It's again an interesting property which says that multiplication by a periodic signal with an exponential will circularly shift its Fourier series coefficients by the same, because this is also a periodic. X tilde k is a periodic a signal as well. So this is an important property, and then so this is multiplication by an exponential. If you multiply a periodic signal by an exponential, it is going to shift its discrete Fourier series coefficients by the same amount. This is an important property. Then is the third and the most important property is periodic convolution. It's very, very confusing. Periodic convolution. So we have spent a lot of time in learning about linear convolution. Okay, periodic, because if the two signals are periodic, it means that still you have you can convolve them, and once you convolve them, you get a periodic signal again. So how to convolve to periodic signal is a question, that how to convolve to periodic signal. So if you have like the same x1 of n, x2 of n, and we are saying that if you have x1 tilde of n, and periodic convolution is usually written as this. You put a circle and put an n. This is the period of the signal. x2 tilde of n. So convolution in time is, yes, multiplication in discrete Fourier series domain. So it still satisfy the important property which says x1 tilde of k, x2 tilde of k. So what are the differences? First difference is that if this has to be a period capital N and this has to be a period capital N, had it been linear convolution, so we know the length of the output would be this plus this minus 1. So for linear convolution, the length of the output would be 2n minus 1. But in case of circular convolution, the length will remain n. The signal, this length will remain n. I'll show you how. Okay, I'll show you how. So this is first problematic thing, that this length is not going to change. So the formula for the convolution is, let's say this is y tilde of n is equal to m goes from 0 to n minus 1 x1 tilde of m x2 tilde. We are not using k because k is used as for the frequency, so just to avoid confusion we are using another variable. It does not matter because the summation, variable of summation will go away, but this is the formula. X m goes from 0 to n minus 1 x1 tilde of m and x2 tilde of n minus 1. So now whatever we have learned for the linear convolution, we need to redo all of that for circular convolution. First, remember what we used to say. If you, for example, if I ask you to convolve these two signals, 1 1 minus 1 and minus 2, for example, 0 1 2 3, this is first periodic signal, and let's say second periodic signal is this 0 1 2 3. So periodic means that it is repeating itself, it is repeating itself, it is repeating itself, it is repeating itself, so it is repeating itself, it is. This is what the periodic means. Okay. So first thing is simple, that if it is x1 of n tilde, so x1 of m will be, instead of n you write m, you write m. This is simple. This is a bit difficult, that how to figure out x tilde 2 n minus m. First is x tilde of 2 minus m, means you have to circularly flip it. So if you flip this circularly, these three samples will come on this side and these three samples will come on the other side. So if you draw this, okay, so this will remain here at 0, but this sample will come here, this sample will go here, this sample. So now this is the new periodic signal, 0 3 2 1. 0 3 2 1. Okay, 0 3 2 1, 0 3 2 1, 3 2 1. So this is x tilde 2 n minus m, for m is equal to 0. You have not, sorry, n is equal to 0. You have not shifted it at this point. So it's n tilde of minus m. So now you need to multiply this signal with this signal. Okay, sample by sample multiplication and then addition will give you one sample. And then you have to circularly move. So then you shift. Once you shift it, so this one will come here and will go out. Then 2 will come here, 2 will go out. 3 will come here, and then you again need to do multiplications and additions, and you got to do, you know, all of that we used to do for the linear convolution. It's very cumbersome, it's very tiring to actually do a convolution like this. But then there is a very slick way of doing this, very interesting, simple way of doing the same. And that is again the circle. Draw the circle. Okay, if you are asked to compute the discrete time, the circular convolution, best way is that you draw a circle. Okay, this is your circle, this is your reference. So this is, you put your one signal, you write it like this in clockwise, which is, you are not, the signal which you are not flipping is, in this case, this is the signal which you are not flipping, 1 1 minus 2 minus 3. So you write it like this, 1 1 minus 2 minus 3. And the other signal which you are flipping, you write it in the other direction, the one which you are flipping. Okay, so this is what you are flipping, 0, 1, 2, 3. So you write it 0, 1, 2 and 3. So that is very simple. So this is how you are going to calculate a circular convolution. Write one signal in clockwise direction and the other signal in anti-clockwise direction. Now you multiply them together. So you multiply these two numbers together and these two numbers together and these two numbers together and these two numbers together, and then add them up to get the first value. So if you do that, 0 into 1 is 0, 3 into 1 is 3, 2 into minus 2 is minus 4 and minus 3. So it comes out to be minus 4. This is your first value of the output. Now what you do is you shift. So the 0 will come here, 1, remember? So circularly shift, because this is what the convolution summation says. It's a shift and drag. But now shift is changed to a circular shift. So your shift is no more a linear shift, it is a circular shift. And you know how to do a circular shift, and I can do it here. This 0 will come here. Okay, this 3 will come here, this 2 will go here, and this 1 will come here. And now you need to multiply 1 with 1, 0 with 1, 3 with minus 2, and 2 with minus 3. Okay, so this is our next answer. So 1, 1, 1, and 1, 0, 0, and 3 minus 6, and 2 minus 6. Okay, so minus 12 plus 1 is minus 11. This is your second value. For third value, again, you are going to shift this. So the 0 will come here, this 3 will go here, the 2 will go here, and 1 will come here. Okay, so now you have a 2, a 3, a 0, and a 1. Again you do the same, multiply, multiply, multiply. So you're going to multiply 2 ones the 2, 3 zeros the zeros, or 1 ones the 1, and 0 into minus 2 is 0, and 3 into minus 3 is minus 9. Okay, so you can calculate all, and then you again do the fourth time, and then it is going to repeat itself. So this is how you compute the circular convolution. Then there is another interesting property which is not there for the linear or discrete time Fourier transform, and this property is called duality. The duality property says that you have a periodic signal, you compute its discrete Fourier series. X tilde of k. This is the discrete periodic series okay, so but this is also periodic, so it means that if you want, you can take its discrete Fourier series as well, because it's a periodic signal. So any periodic signal, you can take its discrete Fourier series. It's a very interesting property which says discrete Fourier series of discrete Fourier series, and you will find out it will be something of the original signal, but will be circularly shifted and multiplied by n. So discrete Fourier series of discrete Fourier series will give you a flipped version of the original periodic signal multiplied by capital N. So this is also an important property which says a duality property. Okay, for example, if I ask you that this is a periodic signal, 0, 1, 2, 3, 0, 1, 3, 5. Let's say this is what we have. And if I ask you to take its discrete Fourier series, whatever answer you get, again take discrete Fourier series. So, and then tell me what is the answer. So you got to flip it. So again, easier way of flipping it is you write it here 0, 1, 2, 3, 5. And instead of reading like this, you read it like this. So it is 0, 5, 3, 2, and 1. 0, 5, 3, 2, and 1. Okay, and then multiplied with n. N is what? N is 4. 0, 1, 2, 3 and 4 it is repeating. So into 4, into 4, into 4, and this becomes 4. So this becomes 20, 12, 8 and 4. So answer is discrete Fourier series or discrete Fourier series is this answer. So you can easily calculate the answer. So good. So but you know, are in signal processing, are we interested in discrete periodic signal? My answer is no. I have zero interest as a DSP person. I have almost zero interest because I don't deal with signals. They are discrete and periodic. Usually in signal processing, I don't deal with these type of signals. I deal with voice, I deal with data coming from the sensors, I deal with all kinds of signals, and all these signals are aperiodic. They don't repeat themselves. So then what is the point of studying discrete Fourier series in this course? Now let's understand the rationale of the book using this to teach you discrete Fourier series. Look at this formula, okay? This is the formula for, these are the two formulas which I wrote, okay? This is x tilde of k for discrete Fourier series, and this is inverse discrete Fourier series. And now look at the formula that I put on the, once we started the chapter, that once we try to discrete discrete time Fourier transform, we get a formula, this formula, which is exactly similar to the discrete Fourier series formula. Summation xn exponential minus 0 to pi over n kn, sorry, there has to be an kn, exactly this formula, okay? And same is the case with inverse formula. They are the same formulas. Why should I care? I need to care because this formula tells me that once I compute x tilde x of k, it is periodic, which is fine. I know that Fourier's transform is periodic, but this is problematic. The problematic is this formula says that if you calculate it for capital N plus capital N, so you can still, once you put a value of n equal to capital N plus 2 or capital N plus 3, still you can use this formula, and you will find out once you use this formula, it will generate this as a periodic signal, x of n. So x of n is not a periodic signal, but this formula has this limitation, and that the process of discretization, it has changed the character of this signal to be a periodic signal. Though I am only concerned with the signal from 0 to n minus 1, but once I go beyond n minus 1, you know, I find out that signal repeats itself. So why should I care? Because I am only concerned of getting back my signal after I do discrete Fourier transform. I can get by my signal by taking inverse discrete Fourier transform. Why should I care? I only care because now these two formulas are the same as the formulas of the Fourier series. Means these two formula considers this signal to be a periodic signal and this to be periodic. This is already periodic, but this signal to be a periodic signal. The formula considers it because this digitalization of the formula has basically changed the character of the signal to be a periodic signal. So as long as you know it is still giving me an answer, I should not be worried. When should I worry? Because now all the properties of the discrete time Fourier transform, these properties have changed their meaning. That is very dangerous. Linearity is okay, but now this property which says that if you shift a signal, it is multiplication by an exponential is no more valid for the discrete Fourier transform. Now this property has changed, and now it has become a circular shift because a linear shift property will not apply on the discrete formula of the Fourier transform. Similarly, this property has changed. It is a circular shift in K, not the linear shift as we have done here. So the frequency coefficients will rotate and come back as if they are moving in the circle. And the most dangerous is this property. We love to compute Fourier transform. We love to compute convolution by multiplying by taking the Fourier transform of the two signals and multiplying them together and then taking the inverse Fourier transform. This formula is no more valid. Now what is valid? That once you multiply the discrete Fourier transform, what will happen? That as if we have actually performed circular convolution, and you know the circular convolution is very different than the linear convolution. First, its length is different, the values are going to be different, so you get a wrong answer, and we never want to get a wrong answer. So this is the problem with the formula or discretizing the discrete time Fourier transform. So you got to find out a way around, So you got to find out a way around that these properties should remain valid, because I have zero interest in periodic signals, in signal processing, but I have no other way but to digitize the discrete time Fourier transform formula, to use it, and as soon as I discretize it, it changes the character of my signal x of n. It assumes it as a periodic signal. Because of this assumption, all the properties which I have been very comfortably using for discrete time Fourier transform are no more valid. They have changed their character. The linear shift has changed to circular shift. The multiplication by an exponential is changed to circular shift in the frequency. And the most important, convolution is no more a convolution in time. Rather, it has become a circular convolution in time, which is equal to multiplication in frequency. So I think let's take 5 minutes break, and then we come back and start studying from here.